one of the extensively. We have to have testimony from IISc and tell us about this piece of the theories on AdS2.
Thank you. Yeah, thank you for this invitation and also changing the dates to accommodate me. So it's nice to be back. And I think after COVID, I mean, the in-person talk was the first time I'm coming and giving it. I was there just a few months ago. So yeah, it's nice to give a talk. So I'll be talking about this work since many of you I've been talking to you. Many of you, every 2 or 3 months we meet, and I the last talk was just a few months ago. So I thought this you have not heard. It's slightly older. So I don't think you have heard this. So I thought I'll talk about some older work. This is with Gava and Rajesh Gupta and Narayan. So it's based on some this work, the latest of it, and it builds upon these older works. So let me just introduction. Yeah. So as we all know here, that AdS2 as a background occurs in many physical situations, near horizon geometries of extremal black holes, including that of supersymmetric. These black holes can be asymptotically flat in such cases, for instance, or in AdS. In such cases, the geometry near horizon becomes AdS2 times a sphere. Or it can be like black brane solutions in which they can become geometry is AdS2 times in a plane of flat space. So for studying near horizon geometries of black holes, this is sort of the canonical geometry which one sees in the extremal case. It also occurs in extremal Kerr black holes. The isometries occur, they're not exactly AdS, but isometries occur. And now, very recently, I think these authors, as well as several others, the AdS2 plays a very important role in this near extremal dynamics as well. So what, I mean, one is interested in usually the black hole entropy or its partition function. And in such cases, you would like to count the degeneracy of states. And for that case, for that situation, we need to, evaluate the partition function of string theory on this geometry. And Ashok has given us, a method in which a suitably defined partition function of string theory in the near horizon geometry, which is AdS2, can lead us to evaluate the degeneracy. So as part of this computation, one has to evaluate one-loop determinants of various fields in AdS. So this is one of the sort of stuff we have to do. Take the geometry and evaluate one-loop determinants around it. And in this context is what I'm going to tell some observations about one-loop determinants. And what we will show, I mean, these are very simple observations, but this somehow they were not carefully looked at, and they play an important role, especially in the supersymmetric context. So what we show is we take partition function of free fields on AdS2, and we'll show that they are not smooth functions as smooth functions as functions of masses of these fields. Expectation values of these fields show kinks or jumps, especially when one dials the masses across the BF bound. And the scale of these jumps, I mean, and we will show it's different from that of a field becoming massless. So the scale of these jumps or kinks depends on the scale radius of AdS2. Okay. So, and this cause of this phenomena, we will track down the cause of this phenomena, and the cause of this phenomena is same as that of imposing normalizable boundary conditions, as this particular reason, which was seen in these papers, that if you impose normalizable boundary conditions on AdS2, it breaks supersymmetry. So we'll come to this connection later. So first we will just look at very simple, I think all of you must be very familiar with this, just bosons on AdS2. So here's the Lagrangian, just free bosons on AdS2, free massive bosons on AdS2. Here's this action and Euclidean AdS2, and this is symmetric. And what we need to evaluate is the free energy of the scalar, which is basically trace log of Laplacian on AdS2. And we study it as a function of the mass. So it's as simple as that. But to dial the mass, what we will do is we parameterize the mass like this, So this is parameterizing above the, it parameterizes the deviation from the BF bound, which is -1/4. And the first term basically ensures that, this term X ensures that we are away from the deviation above the BF bound. And if you look at this iterative dimension, this I think you can relate, many of you can relate to the dimension of the dual operator in this case is this following expression. And if you plug this parameterization inside, you will see that we are always above the BF bound, but we can approach it as X equals 0 on the BF bound. So, so as X varies from positive reals to negative reals, M squared saturates the BF bound at X equals 0. But we always stay above the BF bound. So what we want to do is basically study the partition function at around X equals 0. So for that we evaluate the free energy of the scalar, and we one of the physical quantities we evaluate is the expectation value of the phi squared, and that from the partition function you can see that if you differentiate, if this is in the exponential, if you differentiate with m squared, you'll bring that phi squared downstairs, and you will be able to extract the expectation value of phi squared. Of course, because there is a volume of AdS2, we have to divide by it. But this, because also AdS2 is a homogeneous space, and this expectation value will be a constant, so the volume factors out, and we can just evaluate this particular quantity to read out the expectation value of phi squared. So I hope it's okay. It's simple. So we just differentiate with m squared. M squared is related to the x by that parameterization, because m squared is x in terms of x, it's x dx, and so it's this particular expression.
Just earlier you said that you will be something about crossing the BF bound, but do you mean? You're always above.
Always above the BF bound, but it reaches. It flips sign. I mean, the parameterization x flips sign.
M squared doesn't know about that.
M squared doesn't know about it.
The delta also doesn't know.
Delta also, but the partition function knows about it.
But what is x?
X is just the deviation from that. So
but this on this slide, everything depends only on mod x.
Right. So with that reason,
x?
so because of the fact that it depends on mod x, I mean, finally that is the reason. Because of the fact that it depends on mod x, derivatives of which will have difficulty. Discontinuities.
But for example, it doesn't know about which one is negative, which x is negative or which x is positive.
Right, but expectation value of phi squared, for instance, is sensitive to that, to the derivative.
But that's what I'm missing. Like where x appears in the theory, in the Lagrange, I mean, where?
Yeah, it appears as mod x all the time. Right, so when we dial across x.
But then I could just rename mod x as y, and it's a variable in the semi-infinite line.
So that is you could do that, but even if you vary that and differentiate with respect to that semi-infinite line at x equals 0, there will be a difficulty.
Yeah, that sounds more like what happens with polar coordinates.
But we'll come to it. Actually, I'll see. We'll come. Why I'm parameterizing like this also will be clear. In supersymmetric theories, this is how the deviation comes.
No, I understand, but does something depend on x rather than mod x? That's the.
No, everything depends on mod x.
The only dependence is to the mass, right?
To the mass. You'll see how the mod x actually figures out. I mean, it comes. Let's wait for it.
When m square is less than the BF bound, it diverges.
M squared cannot. I mean, So then it becomes complex and it is tachyonic.
Right.
Tachyonic. Tachyonic.
Divergent.
You can probably divide it by side. C base descent contour, but still. Right.
There'll be an I.
So maybe is it fair to say that if you compute the partition function as a function of x and analytically continue it, then there will be a similarity at x equal to 0?
You don't need to. You can stay in real. You can stay in the real, but let me just show you the plot. I mean, immediately show you the same.
So just one. What is volume of AdS2? No, the next one. It was the volume of AdS2, you are saying it cancels or it doesn't?
Eventually, it will cancel phi squared because f is extensive.
Oh,
Free energy is extensive, and then it will cancel. It will cancel. So we'll evaluate the partition function numerically first because it's quite a subtle thing. So I mean, as we have discussed already, we'll just do it numerically first, and then we will do various. There are three methods we will do this partition function with. So first we will do numerically. Then we will do using the exact Green's function and use the point split approach. Then we will analyze the Green's function mode by mode. Mode by mode, I mean by mode by mode in this angular direction, because there's an isometry in the angular direction. And then we will see how the discontinuity arises. I will track down where the discontinuity is arising. So all three approaches.
The partition function directly, the determinant.
Yeah.
That's why you want to compute it.
Yeah, so there is an integral, for instance, there's an integral which is hard to do. I'll show you the integral, so all three approaches leads to the same. And in fact, extracting this dependence is harder. Maybe there will be some aspects of it, like logarithmic divergence and all can be extracted out. So all these three approaches leads to the same expectation. So first numerics, because it's a subtle question as we have asked. So just numerics, we will just do the numerics. So we evaluate the partition function like this. So for this, we need to know the spectrum of the Laplacian, right? And that is known in AdS spaces, it's known. So the AdS2 admits, so here also this normalizability is important. The fact that these wave functions are normalizable at R goes to infinity. And these are the wave functions. They are in terms of some hypergeometric functions. And the thing is that if you take R goes to infinity, they go like e to the power of minus R by 2 plus minus I lambda. That's the spectrum parameter. So they go like that. So therefore, if you do integrals of this kind, d squared meaning d theta, d phi, d theta, d r, root g. Pi squared, these are normalized. So that's root g has a sign hyperbolic because that's part of the metric. And this grows, and this fact that this dyne kills it. And so that's why these are normalizable wave functions. And they satisfy the Laplacian and so on. And the lambda spectrum.
I lambda log R or just I lambda?
I lambda. I lambda. I don't know the next term. There could be log terms in there. I don't know I don't remember now the next term. Yeah, but these are normalizable. In terms of.
So that's true. But there has to be some lambda dependent, non-trivial lambda dependence in the function, right?
Because of the exponential. Yeah. You mean here?
No, lambda should multiply something.
Yeah, lambda should multiply some.
Lambda.
I lambda log R will do a problem. Because
I lambda log R.
yeah, that's right.
Yeah, sorry. Yeah. Oh, in fact, no. Let me say write it carefully. I forgot half. Yeah, R is there. Forgot to write it. So half. R sits outside. Outside. It's like waves there, and then this is the damping part of it.
It's not log.
It's not log. It's just this. Yeah. So I didn't understand what's the word. So then the wave function satisfies this Laplacians equals 0. And this is the spectral parameter. You can see that quarter L squared is coming here. And for this T is basically the angular mode and so on. So then to evaluate the partition function, it's convenient to look at the heat kernel. So we look at this particular object. So this is at 2 different points. And then you sum up, you fold this wave functions at 2 different points, and you fold the eigenvalues here and perform this integral. And now, but for the partition function, we need to take the coincident limit because it's a trace. There will be a trace in the partition function. So we need to take the coincident limit and integrate over the position. And since AdS2 is a homogeneous space, we take this point to be the origin. So if you look at the origin, these wave function, all of them vanish except p is equal to 0. So all the wave functions vanish except p is equal to 0. So if you put p equals to 0, because of this particular fact, all of the wave functions vanish. So the sum collapses, and we just have to look at the wave functions at p is equal to 0, and that is this particular structure. It has this particular structure. So there's a square of that wave function, and the weights by the spectral weights, I mean lambda squared plus the x squared by L. And then we need to integrate from 0 to lambda. So this is the heat kernel. And for the partition function, you have to do a dt by t of this. And that's the partition function. So log z is given by this. The half is because there's a square root of the determinant. So we take the coincident limit of the kernel, integrate over this volume because we are taking the trace, and perform this particular integral to find the log. So these are standard methods to find the log determinant. So if you
M square is hidden inside K.
yeah. So K, for instance, has this x squared. So this is that Laplacian. Yeah. So because you see, I mean, the Laplacian has this quarter that will cancel that and cancel the m squared, which I parameterize with that, and then the x squared will just sit there. So the partition function is then given by this, and yeah. So here is it, and we are looking for x dependence. So the volume here, you see the volume because of the integral, there is a volume, and the expectation value of phi squared, we have to divide the volume, and so it cancels. So the results in the following free energy. So this is the part which we get by doing this integral dt by t. If you will get the log. Now I'm subtracting this term to regulate this integral, because you see, of course it diverges, and we are looking for the x dependence. And this is the x independent subtraction. So we are subtracting this, and naively from here itself, it's sort of clear that if you differentiate with respect to x, for instance, under the integral, suppose you are allowed to do that differentiation. If you differentiate with respect to x sufficiently, you have a problem, because this will come downstairs. At lambda equals 0, there is a problem because it comes downstairs. Yeah. That's naively. So what we will do is we will perform this integral numerically, and then numerically differentiate, and then use we can use the regulatory volume of the AdS2, but it doesn't matter. It just cancels out. So we don't have to bother about that. This part cancels out. So what we will so we'll take this object. This is the expectation value of phi squared after plugging in everything. We'll do this integral numerically in Mathematica, for x ranging various x's. We have to choose and do this integral with a cutoff at 1000. It didn't matter actually. We changed the cutoff afterwards. It didn't matter to our conclusions. So we sort of change x in the steps point minus 0.5 units, and here is the plot actually. So this is the expectation value of phi squared. As you vary x, and you can see that, the mod structure, I mean, that is the structure here. So this is what we get when you just, numerically plot the expectation value of phi squared.
I still don't understand what it means to plot this. This is the right half of this figure is what you actually can plot, right? There's no such thing as negative x.
Yeah, so that's when you look at the theory this way. I mean, you should just have a look at the theory. But maybe I'll.
So the statement is that as x goes to 0 something, the curve terminates at whatever value.
But what happens, I mean, that's what I haven't connected to the theories we come across. So what happens is that, when you look at theories on, say, AdS2 plus S1 or even S sphere, so these things come like this. They come with a Kaluza-Klein mass, which this extra x squared is n minus some alpha. We'll come to that, the whole square. It comes like this. So here, for instance, you can dial alpha such that you're above or below this n. So the mass, I mean, the structures come. This is x squared. So the Kaluza-Klein masses, when you compactify supersymmetric theories on AdS2 times S2, S1 or S2, is of this structure. So there is a, you can dial the parameter. Such that you're either below or above this particular Kaluza-Klein mode. So I'll show you that those theories in which you can actually dial like that across the yeah. So so let's do this phi squared. So this is numerical. So let's do this phi squared from.
But from that that
Yeah.
equation, the
Yeah.
critical equation.
Yeah.
The signature at singularity at X was clear, right, or not? Because of.
From this, yeah, it's clear.
As you
Yeah,
were saying,
it's
right?
clear. But because it's a subtle fact, because nobody looks at this very much. So that's why, because we were worried about doing the integral first, differentiation and so on. Yeah. So that's the reason we did the numerical integral first and then differentiated, just to show that because it's little subtle thing.
To put it frankly, is it just that even if you're inputting x square into the integral, what appears after you perform integral is square root of it.
So it's mod x, yeah, it's mod x dependent. You'll see the exact functional dependence, and then you'll see actually. So okay, let's do this from another point of view, the Green's function. So the Green's function on AdS2 for a scalar is known. It satisfies this differential equation. Basically, the Laplacian gives the delta function. And it's known actually ever since the initial days of AdS, you can actually read out the Green's function. And here is the Green's function is written in terms of the geodesic length, as expected, because it's a homogeneous space. This is an expression for the Green's function. And delta is that formula for the delta, same formula for the delta. And the geodesic length is related to this. Yeah, this is like basically the geodesic length on AdS2, the inner products of the two vectors and so on. So it's almost, you can imagine if it is just analytically continued, we get this here, geodesic length. So this is the geodesic length. And when it coincides, you see zeta is 1. I mean, when the objects coincide, zeta is 1, just to keep in, sort of remember that when the points coincide, zeta is 1. So if you expand this this object, it's a hypergeometric function again. Nu is the deviation from this part. So if you expand this at the coincidence limit, expand this Green's function at the coincident limit, you get this particular expressions. These are the particular expressions you get. There is this log 1 minus zeta, which has this particular sign. So you can see that log of this term is basically the short distance singularity, because when 2 points come close by, it's basically 2D theory, and it's like massless, so it's log of the r times sine. And then there are these constants, and then there is the psi function, which is the derivative of the gamma function, the logarithmic derivative of the gamma function, which comes, and then suppressed terms, I didn't write, suppressed terms. So if you take the short distance limit, this is the expression, and you can see, like if I subtract the divergence from here, the logarithmic divergence, which is basically the 2-point function of 2D in flat space. So you subtract the logarithmic divergence. Of course, there is an ambiguity in subtracting this up to a constant, but it doesn't affect the x dependence. So if you subtract this and you get this particular expression, and there is this ambiguity, you see that the left, if you approach it from the left and approach it from the right, you get a difference in the slope, and that is this expression. And we actually compare. So if you plot it, of course, from this analytic expression, you get this particular curve. Of course, it should be a shifted curve of the numerics, because there is a constant mismatch, possible constant mismatch. So there could be a shift, and we actually check because it's a subtle fact, because this observation seems to be not very known.
So when you do the difference, that constant goes away, no?
When you do the difference of I say, so for instance, I can here there is a scale R. Okay, I should say this R is dimensionless. So you can put some particular scale here, and for instance, get a extra constants and so on.
Constant, right? But it's constant.
But it's constant. It doesn't depend on x.
Yeah. So when you look at the discontinuity,
it should not depend. It should not depend.
Yeah.
Yeah. When you get this nice pi by L, and you can see also if you introduce the scale back, the discontinuity goes like 1 by L, which is L is the size of the radius. Okay. So when there is no, we'll compare with the flat space Green's functions, right? So when there is no, AdS, the AdS radius is very large, the discontinuity is okay. Yeah. So again, if you plot this up, of course, using the point split approach, this is the answer you get, and there is some constant shift, and you should expect the numerics to work because we just want to be sure, because it is sort of a subtle fact. So we looked at the numerics and we tried to, fitted a constant, one constant, and then and then you sort of plot, and it exactly coincides with the answer, with the point split answer. And so it's plotted together, and we can't even see the difference. But if you take the mole difference, just to be sure, it's like 10 to the minus 6 order differences in the numerics between them. Just to be sure, because So what is the origin of this object? What is the origin of this kink? So the kink is the expectation value.
Let's look at the previous. There's an equation. Top one. So you find that some derivative in x for x positive and x negative, one is greater than the other.
Right, yeah. So it's coming from here, the slope of the psi function.
So naively you would have expected that the slope should vanish because it's a function of x square. And you are saying that doesn't happen. That's just a singular.
That's the thing.
If the slope, the slope should vanish because it's a function of.
It's an even function of x, right?
Yeah, okay.
So the slope should vanish.
Yeah.
But the slope is not vanishing.
Because there's a kink there.
So it's the kink. So what you are finding is the kink. This I think, but I think you can do this even if you never talked about negative x. There's a
that's
inherent meaning of a kink. There's something when you approach, when you reach zero, it
indeed. Indeed. You can talk about it. There. But the way we arrived at it was from theories of this kind, actually, where this application comes in soon.
So previous slide it was still x square. On this slide it becomes mod x, right?
Mod x, yeah.
How did that?
Because you see this delta,
delta
is
mod x.
Delta, and also it's interesting. The scale of that kink is actually L. AdS2. AdS2 is controlling the scale of the scale. So now let's see the origin of this thing. So the kink is arises because
that you have to have some dimensional parameter.
So that has to. But that's what in flat space that's absent. Flat space that's absent. That's why you don't see that actually. Comparison with numerics. The origin of the kink. So the kink, the expectation value arises because we always work with normalizable boundary conditions, and this is the key actually. As this parameter x is varying. Now for that to show that explicitly, so we expand the Green's function in Fourier modes. And so mode by mode, you can solve the Green's function equation. And so this is one, in the radial direction, this, once you go into mode by mode expansion, you just have the radial equation because the angular equation is fed inside one of the parameters of the radial equation. So p squared by sine hyperbolic. So we just have to solve this one-dimensional Green's function problem. And all of us here, I think, know how to solve this one-dimensional Green's function problem. We solve the homogeneous equation. And we impose boundary conditions on the left and the right. And then at r equals r prime, we have to put this kink kind of boundary. We got to put the boundary conditions which incorporates the delta function. I guess all of us have done this problem, right? So here, we have to choose solutions. So let me just have a picture so that the picture is clear. So we have this r. And there are prime here, say for instance, and far away here, this has to be phi, I call it phi out. And the one here is phi in. Here we need to make sure that the Green's function, the wave functions die. And here we need to make sure that the wave functions are smooth. Right? So that's the boundary conditions we have to choose. So that's the phi out and this is the phi in. And the phi out is behaving in such a way that it is normalizable. And the Green's functions are just products of these two for the correct domains, right? And then this WP is fixed by ensuring that it matches this discontinuity in slope. It matches. So this side is clear.
WP is essentially the Wronskian.
Wronskian, yeah. It's related to the Wronskian because there is some sign hyperbolic and all hangs around it. Yeah, it's Wronskian. Yeah. So once you do this. And these are the solutions actually. There is it's solvable of course. And there is this particular solution. And you see, now you can see the difference. When x is greater than 0 and x less than 0, you see there is two different choices of solutions. Because this guy has to be normalizable. Right? You see, at r goes to infinity, this guy goes and the hypersymmetric function collapses to 1. And the exponential comes from there, from this last part, 1 by cosine hyperbolic. That gives the exponential. This goes to 1, of course. And here you see it's the other one. So for x greater than 0, you have to choose this solution. For x less than 0, you have to choose this solution. So that's where the physical choices of the two different solutions are. And there is a similar case for modes with p less than 0. At the origin, we just need to be smooth, and the functions are of this kind, and this is for 0. So we have these solutions. We have the exterior solutions and the interior solutions. We multiply them, and then we can take the coincident limit. So we multiply them, and we take the coincident limit. And using all this, we get the following expansion, short distance expansion of the Green's function. Again, you see that structure coming out. And all this organizes into the flat space Green's function, because that gives you the log of the angles. And the rest are all suppressed. And so we have the zero mode of the Green's function, basically. So you can see that extra term, which is coming for the expectation value, actually comes just from the zero mode. And again, organizing this way, we get the same expectation value that same sort of thing. Now, contrast with the flat space, as we have discussed. In flat space, you would do this for the Green's function. You would just do this particular integral, and this is the answer. And then when you expand the coincident limit and subtract the log divergence, there's nothing actually. There's no dependence, and it's just a constant, and there's no dependence on m. So in this log divergence, the m squared goes inside, and because you have to subtract it with the scale, and that goes inside, and it is not there. We have also, you can do it in many ways. You can do it here using a cutoff also. Put the coincident limit first, and you do the cutoff, and then also there is no that kind of behavior. So the behavior is quite different from that of AdS2. And we have tracked down the behavior actually due to this choice of this boundary conditions. So there's nothing. So let's do it for the fermions now. Now fermions are a little bit more drastic actually, the discontinuity. So again, we have two actions. We have two actions because of a connection with the supersymmetric theory, but the results are the same for both the actions. One is just a massive fermion, and one is a mass structure with the gamma t. You see, 2 dimensions. We have two gamma matrices, gamma 1 and gamma 2. Okay, I've written it in this form, which is the conventional form for writing in 2 dimensions. And the gamma t is the parity. So the two kinds of actions. This action is when just the Dirac operator with a mass, and this is a Dirac operator with this extra term coupling like this, which comes in supersymmetric theories. Yes.
I had one question about the scalars. So there it seems like the discontinuity, like the BF form is, so scalars have this spectrum which is continuous, right? And then there is some gap usually. But when you saturate the BF bound, that gap goes like the lower bound actually hits 0.
Yeah.
So if there is an eigenvalue which is exactly 0, one might get a divergence in partition function. But here the density of states go to 0. Can one explain that from looking at the
Yeah.
Or is it the same thing?
Looking at the fact that this eigenvalue goes to 0, but there is a density of states and so on.
Density of states also go to 0, but then can one look at some small width near that bottom?
Perhaps, perhaps that's a way of explaining it that way, yeah. What we have actually focused on is just this condition, normalizable condition, because that's what, that's the reason why this is happening. The choice of two different conditions as you vary x, actually. Yeah, it can be translated to the spectrum, I don't know.
But is the source basically that there are a small number of eigenvalues near you?
Yeah, yeah, it could be. You should. It could be like that because if you sort of go into this, yeah. So here's the partition function. It has to be that because after you differentiate it, you see this comes downstairs. This comes downstairs, and then zero. Yeah, that is the contribution which is coming. So.
You change the function from finite lambda, will change, right?
Yeah. Then it won't change. Yeah. If you integrate from finite lambda.
No, I'm just saying the density of states.
Make
the lambda into real 0 here are unchanged, but suppose you just arbitrarily change
at high
lambda or
it shouldn't change.
This singular will be
that is seen also because we did a subtraction at large lambda. We see written that and it didn't affect that. Yeah.
When you were talking about normalizable boundary conditions for the two cases, one had x and the other had
minus x. For x greater than 0, let me show you that again. For x greater than 0, it is this. For x less than 0, it is this. This is also positive.
But so far mod x was appearing everywhere.
Yeah, it is mod x. This is mod x actually. But I've written it very explicitly. Right? Because x greater than 0, it is this. X less than 0, it is.
If you write it as mod x,
yeah.
Then there will be no switch.
Yeah. But we know that we are solving a differential equation with two solutions.
Yeah.
And the switching
one solution.
Switching from one solution to another. Yeah.
Also inside of the hypergeometry.
Yeah. So that is also mod. You can write it like mod, but it is actually switching two solutions in this differential equation. And that is what I think in the supersymmetric theory is sort of crucial. So we have this contrast. And now the fermions, which is it's more drastic. You have this two cases, both the cases lead to the same result. And we can look for the expectation value of psi bar psi from this action because you just differentiate with m. And you can differentiate the other one with m and we get this particular expectation value of bilinears. Okay. And the second action, as we will see, naturally occurs in supersymmetric theories. And both the result for both are identical actually. So again, we go through the same algebra. So the first action has b slash plus m. Since there are equal and opposite pairs of eigenvalues, you can convince yourself a little bit of convincing that this determinant is same as this determinant, and then we can write it as the square root of minus b slash squared plus m squared. And again, we can define the free energy as log of that and read out the expectation value. Same principles. And for the second action also same. When you take the square, it turns out up to a phase, it turns out to be the same partition function. And again, differentiating that, we can get this expectation value. So here are the fermions. These functions are also known. The Dirac operator on AdS2, the functions are also known. There are also some hypergeometric functions and so on. For p greater than 0 and p less than 0. So these are normalizable spectrum, and they satisfy this. You can see the two sort of eigenvalues, plus and minus, and gamma 3. You see that sigma 3 actually shifts. The gamma t shifts between these two eigenfunctions. So we have this. Similarly, for the negative half integer along theta, there are some functions of that kind. So the spectrum is known, and they have the important thing is to know that there's positive and negative eigenvalues, which is what led to the in squaring the determinant and so on. And when you consider the heat kernel, this is the answer for the heat kernel. So the two eigenfunctions, this is for p greater than 0, actually it's for p less than 0, but it's written in this form. So, so p full p, and the sum over the two eigenfunctions, and this is it. So this is the sort of heat kernel, and again we take the coincident limit and look at the origin. And again, there is this nice property that at p equals 0, this object is non-vanishing. This is the only object which is non-vanishing. You can see from structure, actually, it's the only object which is non-vanishing. And that is what you just have to replace it with this. This has a name in this literature. It's called Plancherel measure. So we put it inside, and yeah, we do this heat kernel integral, and from that find the partition function. So which results in this following integral. So the integral is different. It's a cotangent instead of tan. So and again the same stuff. Similar integral. You can subtract the divergence by subtracting this or the large lambda behavior, and obtain the expectation value by differentiating it with respect to x, which is scaled version of the m. So x is basically m by l. M is x by l. So we just scaled it, and this is the partition free energy, yeah. So once we do this again, we do this using it numerically. We do this integral using numerically, step by step, and differentiate the free energy numerically. And here, yeah. So this is quite amazing actually. So there's a step discontinuity in this expectation value at x equals 0 at that point when the mass changes sign. And in fermions, the mass, people have different signs also in this case. So, so when the mass changes sign, there is this jump and unit jump. In this unit of pi L, it's a unit jump actually, and we can sort of try to vary. Yeah, here is the expression. In our numerics,
just in our theory, it's expected to be an odd function
for this
of mass because we differentiated once.
Yeah, I differentiated it once. Yeah, this.
And then that would have been meant that it's 0.
It's 0. Yeah, it should be 0. Yeah, yeah. In fact, in flat space it's 0. Flat space it's 0. Yeah, that also can be seen from this expression. If this, if you trust this, if you take the 1 by L and L goes to infinity.
Justin, in this case, just remind me, how did you define x? Is it the same?
Yeah, it is just linear in mass.
Yeah, let me just see the
Just that.
Oh,
here the fermions, the mass comes linearly.
yeah.
Linearly.
No, because here, I mean, this is a very different story because the positive and negative mass does have a physical
physical meaning. Yeah, even without supersymmetric context. Just as a meaning.
Without AdS2 S1. It gives the kind of helicity or something. So,
so and this drastic, surprisingly, it's not being noticed. I mean, so, so we can.
This is strictly an AdS2 phenomenon.
AdS2 phenomena. I mean, higher ones, I think more derivatives have to be taken because that Plancherel measure increases. I mean, its weight increases, I think, more derivatives. I mean, this is most drastic in AdS2. So again, you can do the similar thing for the fermion bilinear, and surprisingly, the fermion Green's function are not seen very much in the literature in AdS. It's not seen to solve this Green's function. So we take the one with the gamma t because that connects with supersymmetric theories. I have 15 minutes. Okay.
The time is up.
So it connects. So connects with supersymmetric theory. So we looked at this Green's function, and there's only a few papers actually talking about fermionic Green's function and AdS in general. But this is one of the authors, and the way to go about it is actually like make an ansatz of this kind, and these are functions of the geodesic distance. And this is like the one which takes parallel transports between one spinner to another spinner, because these are bi-spinner objects. So this is that object. And so there is this geodesic distance, which is related to this same geodesic distance. And we just have to plug these, so this geodesic distance has, what is this eta mu? Is basically the tangent along the geodesic, that's that. And the parallel transport obeys some equations of this kind. So it's a little involved, but it can be done. And the equations that scalars for function, I mean the parameterization, alpha and beta, they satisfy this equations. And alpha satisfies the second order differential equation of this kind. A, B, and C are these cosines and in terms of the geodesic length. So finally you can reduce it to the second order differential equation. And again, there is this choice of the solutions. Alpha is this and minus. There is when the M switches sign, there is this choice of solutions. And and one of the constants can be fixed by demanding it behaves like Green's function in flat space. And so we can fix the Green's function completely. And once we fix the Green's function, we do a short distance expansion of all this. And you can see the psi functions coming again into this thing. So we have all, and then we evaluate the psi bar psi. Same procedure, it's a little more involved. We evaluate the psi bar psi and we remove the flat space divergence, and we get this particular expression. And then you see that, you have this particular form. This is some constant which can depend on the regulator, but this structure is there. And if you take the m going to 0 limit, it goes as 1 by Lm, this structure. And then m times that will obey the same discontinuity which we saw in the numerics. You can see that again. So you have this, as m goes to 0, it has this 1 by Lm structure. And then when you multiply this m, so that m by mod m comes, and then you have that discontinuity structure. So this result agrees again with the numerical evaluation of the partition function. And the discontinuity is not affected by the ambiguity. And again, for the psi bar psi also, if you proceed, you will get the same result. It disappears as we kept on discussing. When you take L going to infinity, the discontinuity disappears. So again, just to contrast and that discussion which we followed up, when you take on the flat space and when you do it, there is no discontinuity, it just vanishes at that point. There's no discontinuity there. Similarly, both ways of doing it, there's no discontinuity. So now I will connect it to the supersymmetric theories. This observation actually came about by actually trying to study localization on non-compact spaces. And so we look at this chiral multiplet. So chiral multiplet is similar to the chiral multiplet in 4 dimensions, but dimensionally reduced. So there's a complex scalar and a Dirac fermion in 3 dimensions. We look at the partition function on AdS2 times S1, right? And this, because of this phenomena, it is not a smooth function of the ratio of the radius of AdS2 to S1. So this is the metric, and this parameterizes the radius of S1. This parameterizes the radius of AdS2, and there are, because it's a rigid background, there are certain set of killing spinor equations you have to satisfy. And so these are the killing spinor equations, and there are some background fields because of the rigid AdS2 times S1 background. There are some background fields you have to turn on to ensure that we have the supersymmetric killing spinors. And here are the killing spinors. If you find the killing vector from here, it generates along the compact direction only del by del theta and del by del tau, which is what generally one uses for localization. And you can see one aspect of the killing spinor, which is quite crucial. Like you see, the killing spinor grows. It grows at R goes to infinity. That is a very typical feature of AdS. It grows at infinity, and that is what spoils many of these nice normalizable properties. So it grows at infinity. So if you take the chiral multiplet of this, and just on this background, which is a supersymmetric background, there is a killing spinor. And plug in, this is the action. there's a complex scalar, a Dirac fermion, and certain backgrounds which are there, which are all given. I mean, the backgrounds are all given to you, and then you just substitute it in the action, and the action reduces to this form. Yes.
How is it? How is the background supersymmetric here?
No, the background as such before quantizing. Just there is a killing spinner. That's all I'm saying. There's a killing spinner. So the killing spinner is just existing. Yeah.
But that is not normal.
Yeah, that's not normalizable. Yeah, the killing spinner is not normalizable. Yeah,
that's even in flat space, the killing spinner is not constant.
Yeah,
That's not normalizable. But the real question is whether it relates normalizable modes to normalizable. I think that also fails here in some cases.
Yeah, in the window, that's what that jump. So all it's unlike the case I mentioned, unlike the case you studied, in which it's always not. Always maps normalizable to non. I'll come to that.
The constant part annihilates the things and it like.
No, it's like if the killing spinner goes to a constant, suppose in flat space, right? Then if you have a bosonic mode which is normalizable, then acting on that it will produce a harmonic mode which is also normalizable. Right?
Yeah.
The exponential growth is what is
it's a problem. Yeah.
Problematic.
Yeah. When you quantize the theory, when you try to do a one loop determinant, for instance, So the killing spinner. So once you calculate this action, and then you because we studied the phenomenon on AdS2, so we decompose this in Fourier mode along the S1. And when you decompose the bosonic part of the S1, so here is what I said. The bosonic part of this, the supersymmetric action. So you have the usual root GR del phi, and then you have this mass term, and this mass term is of that form. So n by u was the radius of L is the radius of AdS2, and u was the radius of S1. So it comes in the structure. This is the X which I was saying, and it parameterizes. It comes in that form, at least in this particular class of theories. It comes of this form, and then there is a thing which you can do. You can dial this, and you can cross inside. You can cross positive and negative. So it's clear that from our previous discussion that whenever this ratio becomes equal to an integer, equal to the integer of the Kaluza-Klein mode, there will be a problem with this partition. And that itself sort of tells you something, because in supersymmetric theories, you shouldn't have these problems. You shouldn't have jumps, and you shouldn't have it should be smooth. So whenever this moduli or whatever backgrounds are dialed, and you have this particular, it's not smooth. If you do the same thing for the fermion, so this is the point, it's good to know this. Delta is some R charge of the phi field. And so whenever this becomes integer, it becomes a problem. So when you have fermions, you again decompose it along the S1. You can impose periodic or anti-periodic, doesn't matter. We'll do periodic most of the just like transparencies, because we talk about supersymmetry. And the action becomes this. And you see, it is that class of actions we considered with the I, with the gamma T, which is the chiral part. This gamma 1 and gamma 2 are here. So it reduces to that. And whenever, and X can be identified with this, and whenever this ratio becomes of this kind of an integer, the partition function of fermions has a expectation value is a discontinuity, partition function is a kink. And but you notice one thing, you notice that this point at which this becomes integer is different from the point at which the fermions become integer. Fermions have a problem. So the points are separated, and this is just a claim that at that point the discontinuity is there. Now the discontinuous fermions occur at different values of the ratio, and this observation relates to the supersymmetry in the quantum theory. So say we took R not equal to 0 for periodic boundary condition.
So fermions and bosons jump at
different points. Different points. And that is the reason that there will be some interval in which the boson has become from normalizable to non-normalizable, and the fermion remains put. I mean, and the supersymmetry relates the modes, and that's how I will indicate it a little bit carefully. So, so the discontinuity fermion determine occurs at different values, and this observation relates to the supersymmetry. And suppose supersymmetry relates, in fact, we have done it in a detailed analysis. We discovered this actually by doing the the supersymmetric problem. So, so suppose supersymmetry relates the modes phi n to psi n, and this is the first class of normalizable modes, and the first other class of the first class of solutions to that equation for the Green's function, and this is the second class of solutions to the equation to the differential equation. So these are the two solutions at radial infinity of AdS2. And consider the case in which we actually want to impose normalizable modes. Now, if the Kaluza-Klein mode n, so we are running over the Kaluza-Klein modes. If the Kaluza-Klein mode is n, which is less than that particular thing, so the boson, these are the pairs of bosons and fermions, which are related by supersymmetry. But when the Kaluza-Klein mode is in between, this is delta without the minus sign, sorry, without the minus sign. So when the thing is between this, actually this mode switches. This mode switches to the second one, while this stays like that. And here is where there will be a problem with supersymmetry. And when n is greater than that, both of them switch, and then we have this particular.
Sorry, in that middle region, one is normalizable and one is not.
One is not, yeah.
But then if the supersymmetry, if the killing spinner is also growing, then it can do that. Right? That's
It
what
can do,
happens.
it can do that. That's how it's happened.
Would you call that a problem with supersymmetry, or
Yeah.
that's what supersymmetry is supposed to do?
Supersymmetry, it's supposed to do with supersymmetry, but if you want to quantize the theory, you have to have only normalizable modes.
Yeah.
Supersymmetry should really normalizable.
Normalizable.
Sorry, yeah.
Yeah.
In this case it does.
Yeah.
But in the first and the last cases it still does.
It does, yeah.
So I see.
Sorry, so for that range, there is an issue with the black.
No, this is not black. This is this is some model theory of AdS2 with a chiral multiplet. In black hole, it's always
everywhere.
Yeah. I think that was later than this. I think Ashok has a paper. I think. Yeah.
Supersymmetry, they cannot realize.
Yeah.
So that counts as supersymmetry.
Yeah.
Right? But the fluctuations don't seem to be adverse.
Yeah.
So that's why applying this localization method on black holes seem to be very shaky now. You can't realize supersymmetry on the modes.
Yeah.
But sorry, just about the first and last case.
Yeah.
So your killing spinners are exponentially growing, right? As you said.
Yeah, here we are not bothered about the supersymmetry actually. We're just imposing normalizable boundary condition in this class.
No, but supposing I do look at the first class.
Yes.
So one means normalizable, right?
Yeah.
So both are normalizable.
Both are normalizable. Actually, here all of them are normalizable in this window.
Oh, I see.
Because I've switched it so that it becomes normalizable.
So that okay. But then how does supersymmetry?
Yeah, supersymmetry is not preserved actually in this particular window.
Yeah, because supersymmetry is 1 to 1. 1 to 1. One supersymmetry relates 1 to 1 and 2 to 2.
Yeah, that's what I'm asking. So in the first line, supersymmetry is there, right?
Yeah, yes.
So I'm just asking that in that first line where it is there, the killing spinner does grow.
But still, this has enough leeway to.
Yeah, so I'm asking what is that leeway?
That
So
L,
this
I mean, this
small-
parameter.
Yeah, since the bosonic thing is falling off faster now.
Yeah, so it's falling off
Even-
exponentially and faster.
Faster,
than
yeah,
the
because
charge.
Yeah.
There's this I
You can still
delta.
have that
Yeah.
one supersymmetry generated.
But then certainly one of them will fall off much sort of slower.
Slower, yes.
Oh, that is true.
Yeah. So, but in the if you want to impose supersymmetry conditions, this is what we have to do.
Right.
I mean, you have to choose this and this actually, yeah. So, but that's not what we do for quantizing the theory. So therefore, the supersymmetry is broken in the quantum theory, and it's not because it's not compatible with normalizability. And the analogous. It's not like a drastic thing about supersymmetry. It's just that it's like thermal boundary conditions. If you have thermal boundary conditions, you know supersymmetry is not. It's of that kind, I think.
Sorry, but I thought you had periodic boundary condition.
Yeah. So you had periodic. I'm saying this problem of normalizability is similar to that because because it is like you put it on a particular background like AdS, it breaks it. Yeah.
Can this be seen in the thermal partition function of the
Generalized
region?
Nice. Yeah, I mean, let me finish and tell you. So, yeah, so, maybe, I mean, I don't know, we haven't explored this. Maybe we should quantize the boson alternatively in that, because, it's a choice of different boundary condition. And if we can quantize the boson with a different boundary condition by introducing certain boundary terms, perhaps we can. Okay. So we have done this for the hypermultiplet. Let me finish. I'll come. So when we sort of look at hypermultiplets on AdS2 times S2, the similar form is there. So similar, same phenomena. In that case, backgrounds can be chosen. Even in this AdS2 cross S2, we can choose certain backgrounds so that supersymmetry is there. Like the theory starts out being supersymmetric. And there are some backgrounds you have to take care of. It's a little involved. And so the masses. So what we have shown is that if you dial various ratios, so there are two ratios: the radius of AdS2, there are two length parameters, radius of AdS2 and S2. And if you sort of dial the ratios to this particular point when they are integers, then the expectation values of the fermions and data. The bosons always remain above the BF bound. So the bosons have no problem, but this fellow has fermions have a problem in this particular case. So let me just conclude and we can discuss. So this analysis indicates that the methods of localization can fail when the theory is considered on AdS2 process. The serious and more, the failure is more serious as we were discussing in the AdS2 times S2, where these conditions always break supersymmetry. Actually. In fact, n equals 2 gravity multiplet is what you looked at, I think, in that case. And we should actually re-examine these localization geometry, methods in these near horizon geometry, and perhaps working with certain class of boundary terms to ensure that we choose the correct boundary conditions for bosons might help. So I you're saying generalized free field. I mean, meaning just the correlators involve just 1 by x minus x to the power 2 delta. I mean, that's kind of periodic. Whether it sees there. Yeah. So in position space, we know the correlator, and the question is the partition functions of those. Whether it has 2-point function and then the finite piece of it, whether it has some problem. Yeah, you are asking in context of holography, right? Because I don't know.
In higher AdS also similar problems.
It should happen, but it's at higher level. I think. I mean, supersymmetry of course is broken. I mean, most likely it's broken. But this partition function jumps might happen much later. I mean, because we have to differentiate. I think.
But this supersymmetric breaking is also a little strange. I mean, equal for super young system. That's something.
I know. Yeah, that's why I was asking the same question when Cyber was there. I mean, and he admitted that it should break, but how to handle like n equals 4 theory is on the boundary, and then you have the bulk AdS side, and then how does it? So most probably there are boundary terms which we need to be aware of. I think.
In AdS2 times S1 black hole, there are a lot of supersymmetric black holes around which scalar fields set.
Yeah, but here I think the point is given beyond that. If we just take n equal to 4 super young base and look at the Billings mirrors in AdS5, right? That's vacuum AdS5. And then they also have exponential growth as we go towards the
Yeah.
Right? AdS always has this exponentially growing Billings mirrors at the moment. And the question is, given that there is always a range at that, not all the normalizable modes will become non-normalizable ones after you see these mirrors. Right? You have to work examining the.
That's what one of the AdS5 we looked at, and somehow Samir claims it's good actually, but we couldn't repeat it.
Because they are applying supersymmetric localization also on this.
On this, it's a bit it's sort of. I mean, the reason I don't present most of the time this results are because we don't know how to go ahead. I mean, like, okay, we have to go and study certain boundary terms or something. How to solve the problem is it's not clear actually.
So this phenomenon you were seeing as you vary the relative sizes, right?
Yeah, the relative sizes. Yeah.
If AdS5 times is 5.
Yeah, there we don't. Yeah, even for instance, in this case, which Ashok studied, there is nothing. The radius are equal here. In this case, the radius are equal, and there's no parameter to vary, and it's always breaking. I mean, always. The class which we looked at was a little earlier, and we were trying to hope. I mean, that we were trying to find windows where it works. I mean, that's the reason we were looking at that.
So can you remind me why this happens there?
Yeah, I mean, because first the radius are equal, right? I mean, because it's coming from flat space.
Yeah.
So the cosmological constant vanishes in flat space. Therefore, when you take the near horizon, the two radii are connected, and they're equal actually in this case. And then there is no parameter to vary, and so the killing spinner grows exponentially.
So just
Just that, yeah.
But as we saw, there are some regimes in parameter space where even though you have this kind of
So that's for the theory which we studied. I mean, like this one doesn't have any diagonal parameter.
I mean, one example of this which is for us easier to understand is if you take a gauge multiplet, right? The gauge fields are discrete modes, which are actually square, not delta one. But the superpartners are fermions, right, which are no discrete. So there it's even harder to say how it can be supersymmetric.
That is more relevant.
Even scalars will only have content. Like if you have
Scalars and hypermultiplets, at least both have only continuous modes, right? So there is some hope that in some window there is a.
But wouldn't there be more supersymmetry where you have scalar and HP in the same multiplet?
That could be similarities.
Yeah,
Scalar formula and gauge.
the gauge field. What is it?
There are some zero modes. That they are
like derivative of the scalar. That is
these look like pure gauge, right? But the gauge transformation parameter is not normalized. Right, so that's why you allow them as normalized modes.
So what does this say about black holes like it?
At least the minimal thing it seems to be saying is that applying localization wants to be very careful, right? Because modes are not paired by supersymmetry. And localization uses the fact that the modes supersymmetry has to act on that modes. What it says about black holes is not the background is still supersymmetric, right?
I think the technique to evaluate the partition functions which have been used, we have to re-examine.
I mean, if you directly calculate the determinant, it's okay. You are not using supersymmetry.
Right? Just calculate the
determinant. But if you try to use supersymmetry to manipulate the determinant, that is has to be examined very carefully.
But here it seems that even if you look at determinant, it has some sort of singularity.
No, but in these black hole thing, that diagonal parameter is not there.
No, but as I was saying, in AdS5 times S1 black hole, there is a diagonal parameter. And if you look at one parameter set of black holes, you can dial that one parameter, and there are points where the scalar field becomes saturates the field. So there are discrete points where higher and higher angular momentum moves up. So this is the scalar field.
But it never goes below here. It touches the BF bound and
so it always saturates the BF.
Yes.
So there are a lot of black holes which are discrete set of black holes where this scalar field which is in supergravity that saturates the BF.
And the fermions? How do
Fermions I'm not sure, but scalars definitely there are.
And they have near horizon AdS2. These
These are also
all external. They're all
there.
Oh, there will be a problem there.
Then I'm not sure what does it say about these. Yeah, because people have like matched entropy and so on from the like the.
But that's the saddle point. Then fluctuations. I mean, this is about fluctuations.
Yeah, I mean they don't violate the VF norm, so but still they settle it. So I was wondering if there is some issue with it.
Yeah, I mean, this is coming of course at one higher order. This is saying that the determinant is not continuous. Which may be okay, which may be even microscopic counting may also have that property, right? This is leading, this is not at a leading level, this is not at a leading level, right? So it is possible that even the microscopic counting may be an interesting to check whether there is similar peaks in the microscopic form.
Yeah. With this goal, we try to examine all n equals 2 theories. Like because n equals 2 theories is a huge amount of black hole solution. It's similar to the n equals 4, but there is like
The index might be able to.
Yeah.
But we couldn't, we didn't compete, we didn't have energy. I mean, we do this like far away. I mean, it's not.
Yeah, and equal to the counting is also.
Yeah, but at least the bulk action, like various classes are known.
Yeah.
Various classes. Yeah. So we could see whether it really exists in those things or not. We were trying to find out. Yeah, we didn't make a conclusive statement there.
When you go near extremality, do you see some?
Yeah, to move the, I don't know how it transfers this property to near extreme. Complex.